In this video, I want to describe the neuron resting membrane potential, which we often just call the resting potential for short. So first let me just draw a neuron that'll be a little distorted, just so I have room to draw. So we'll draw the soma here, and a really big axon coming out of the soma. And normally an axon is a thin, long process coming out of the soma, but I just need a little room to draw, so I'll draw a big, thick one. And then this will be the other part of the soma, or the cell body. And then I'll just draw one really big dendrite. And like the axon, of course, these are normally just these little thin processes coming out of the soma, but I just need some space. So most neurons at rest, meaning when they're not receiving any input, have a stable separation of charges across the cell membrane, called the resting potential. And that consists of more positive charges in a layer on the outside of the membrane, and more negative charges in a layer along the inside of the membrane. And these charges are ions. So the negatively charged ions that are in a layer along the inside of the membrane, we also call anions. And the positively charged ions in a layer on the outside of the membrane, we call cations. And this layer of anions on the inside and cations on the outside goes all over the neuron cell membrane, all through the membrane of the dendrite and the soma, and all along the membrane of the axon. And just to be clear, there is a mix of anions and cations on both sides of the membrane, and I've just drawn plus signs on the outside of the membrane to represent that in the layer against the outside of the membrane there are more cations than anions, and I've drawn negative signs on the inside of the membrane to represent that in that layer there are more anions than cations. And to talk about the size of the difference in this separation of charges, the convention is to call the outside 0. So we just say the outside is 0, and we just kind of set that as the reference. And then we just refer to a single number on the inside of the membrane, which is the difference between the voltage on the outside and the inside, or the difference in the strength of the charge separation. And this difference can vary between neurons, but around negative 60 millivolts would be a really common resting potential for a neuron. So I'll just write a little m and a big V for millivolts. That's the value we use to quantify this difference in charge separation. And around negative 60 would be a really common resting membrane potential for a neuron. The resting potential of neurons is related to concentration differences, which are also called gradients, of many ions across the cell membrane. So there's lots of different ions that have high concentrations outside the neuron compared to lower concentrations inside the neuron, or vice versa. But a few of these ions are the most important for neuron function. The cations, or the positively charged ions, that are most important for neuron function are potassium, and I'll just write that as a K+, sodium, which I'll write as an Na+, and calcium, which I'll write as a Ca2+, because each calcium ion has 2 positive charges. And the most important anions for neuron function, or negatively charged ions, are chloride, which I'll write as Cl-, and then there are multiple organic anions. And so I'll just write OA- to stand for organic anions. And there are a bunch of different organic anions inside neurons and other cells. Most of these are proteins that carry a net negative charge. Now these 5 kinds of ions are going to have concentration differences across the cell membranes, which we also call concentration gradients. And it's different for the different ions if they have a higher concentration inside or outside the neuron. The organic anions and the potassium ions have a higher concentration inside the neuron than outside. So I'll just represent that by having these letters written large inside the neuron, and then I'll write a small OA- to show that there's a smaller concentration of organic anions outside the neuron than inside. And the same for potassium. I'll write a small K+ outside the neuron compared to a large K+ inside, because the concentration of potassium is higher inside the neuron than outside the neuron. And the opposite is true for these other 3 ions. So the concentration of sodium is much higher outside the neuron than inside the neuron, as is the concentration of calcium. There's much more calcium outside the neuron than inside, and the concentration of chloride ions is also much higher outside the neuron than inside the neuron. Each of these ions, therefore, is going to be acted on by two forces that try to drive them into or out of the neuron. The first is an electrical force from the membrane potential, because each ion will be attracted to the side of the membrane with the opposite charge. Opposite charges attract each other, and like charges repel each other. So if we look at each of these ions in turn, the organic anions are negatively charged, so they will be attracted to the outside of the neuron, where there are more positive charges. So the electrical force acting on the organic anions will try to drive them out of the neuron. Potassium is the opposite. It's positively charged, so it will be attracted to the inside of the membrane, where it's more negative. So its electrical force will try to drive it into the neuron. Sodium is the same as potassium. It's positively charged, so it will be attracted to the more negative inside of the neuron. Chloride is an anion, like the organic anions, so its electrical force will try to drive it out of the neuron. Calcium is a cation, like potassium and sodium, so its electrical force will also try to drive it into the neuron. But now the second force acting on these ions can be thought of as a diffusion force, or it's often called a chemical force, related to the concentration gradients across the neuron membrane, because particles in solution will always try to move from an area of higher concentration to an area of lower concentration. So if we look at the organic anions, they're in a higher concentration inside the neuron than outside, so their diffusion force will be trying to drive them out of the neuron, just like their electrical force is. Now potassium's a little confused. Its electrical force is trying to drive it into the neuron, but it has a higher concentration inside the neuron, so its diffusion force is actually trying to drive it out of the neuron. Sodium has matched electrical and diffusion forces because it has a higher concentration outside the neuron than inside. Chloride's electrical force is trying to drive it out of the neuron, but because it has a higher concentration outside the neuron, its diffusion force will be trying to drive it into the neuron. And calcium's just like sodium. Both its electrical and its diffusion force are trying to drive calcium into the neuron. These forces we often call electrochemical driving forces for short, and neurons are going to use these forces to perform their functions. But before we talk about that, in the next video, let's talk about how the resting membrane potential is created and how it's related to the concentration differences of some of these key ions.